Okay, so 2.8 is entitled Algebra of Functions. And what we're going to do is, given pre-existing functions, we're going to show you how to form new functions and how to also evaluate them at various values. So the first one we're going to look at is called the sum function. So we're going to be given two functions, f and g, whatever the functions are, okay? That's not of particular importance at this point in time, but we're given two functions, f and g, and we're going to form a sum function, which is called f plus g of x. And f plus g of x, this brand new sum function, is going to be nothing more than the sum of the outputs of the individual functions. So that's how we form what's called the sum of two functions. It's just the sum of the outputs of the individual functions. We have what's called a difference function. F minus g of x, which is going to be the difference between the outputs of the individual functions, specifically f of x minus g of x. Product function. F times g of x is going to be the product of the outputs of the individual functions. And as you would guess, there is a quotient function. F divided by g of x, which is going to be the quotient of the outputs of the individual functions here. And of course, since we're dividing, we got to make sure that g of x is never equal to 0 for any x, or else the function will be undefined. All right, so ladies and gentlemen, the domains of all these new functions that I'm showing you how to build up here, the domain of all these functions is going to be the intersection of the domains of the individual functions. So the domain of all these functions up here, the sum, difference, product, quotient functions, are going to be equal to the intersection of the domains of the individual functions, or the intersection of the domains of the component functions. All right, so that's your sum, difference, product, and quotient. Now, there is another operator called the composition operator that allows us to form what's called the composition of functions. And the composition of functions is a little bit different than all these other operators up here, which are very intuitive. The composition operator is a little open circle here, and we would read this brand new function as the function f composed with g of x. So f composed with g of x. And what the composition function does is it takes the output of one function and it feeds that output into another function. So f composed with g of x is going to be the function of f of g of x. Caution, ladies and gentlemen, f times g of x, the product function, is not even remotely related to the composition function. So don't get these mixed up. No relationship whatsoever between the product of functions and the composition of functions. Night and day difference. Don't think they're the same, because they're not necessarily, they're not the same. Okay. All right, we can also flip these around and form a new function called g composed with f of x. This is g composed with f of x. And g composed with f of x is going to be g of f of x. So the composition operator, again, takes the output of one and feeds it into another function. I'll show you a picture that helps you to understand the composition of functions in a second. Do we have this page all accounted for here? The algebra of functions.
Not quite. I'm still working on the last little part.
And it's also true that g times f of x is not remotely related to g composed with f of x. No relationship whatsoever, again, between the multiplication operator and the composition operator.
Okay.
All right. So let me draw you a little cartoon that helped me to kind of like understand what this composition is all about here. If we look at the function f composed with g of x, what's that really saying? Well, this picture might help you to understand. I always appreciated this picture and what it's trying to say. Think of a function as being kind of like a machine, ladies and gentlemen. It takes some sort of output, transforms it, and spits it out as some sort of an output. Okay. So this first machine here is going to be the machine g, and the second machine is going to be the function f. So what f composed with g of x does is it takes some value x first and feeds it into function g. So it puts some value called x in the function g. G operates on x according to its definition, and then it outputs something called g of x. Well, g of x becomes the input into the second machine called function f. Function f operates on its input called g of x according to its definition and outputs something called f of g of x. Does that picture help? That's what composition does, ladies and gentlemen. Takes an input, transforms it, provides an output. The output becomes the input into another function. The other function then transforms that input and provides an output. Okay. All right, so, and of course, g composed with f of x would have these switch. This would be function f, and this would be function g. So that's what composition does. Okay, so on page 271 in our textbook, let's go there and see what kind of trouble awaits us. All right, so I'm going to page 271. And this is where the problems begin for section 2.8 here. All right. And I'm going to go down here to these problems 9 through 13. Now it says evaluate the functions. I'll tell you what, before we evaluate functions, maybe we should first of all understand how to even produce some of these functions. All right, so let's jump down to 19 through 21 and I'll go back and get the other ones. It says refer to the functions R, P, and Q, find the indicated function and write the domain in interval notation. So R of X is this linear function called negative 3x. P of X is this quadratic function, x squared plus 3x. Q of X is this radical or square root function of 1 minus x. And they want us to, using these functions, they want us to form new functions. In problem number 20, they want us to form this difference function called P minus R of X. So how are we going to do that? P minus R of X. Well, according to the definition that I laid down for the difference function, P minus R of X is going to be P of X minus R of X. So to form this difference function, P minus R of X, we're taking the outputs of the individual functions and we're subtracting them from each other. But now what was P of X? How was P of X defined? And how was R of X defined? Well, P of X was this quadratic function, which is x squared plus 3x. And then from that, we're going to be subtracting off R of X, which is to say we subtract off this linear function, negative 3x. So therefore, P of X was defined to be this quadratic function, and R of X is defined to be this linear function. So this new function called P minus R of X is going to be this new function x squared plus 3x minus a negative 3x. Subtracting a negative 3x is as good as adding a positive 3x. And 3x plus 3x is 6x. And so there we have it. Ladies and gentlemen, this is the brand new function called P minus R of X. So P minus R of X is this function right here. Questions how we form that function. All right, now, what is the domain of function P? What is the domain of function P? Well, function P is just a quadratic function or a polynomial function. And I think I indicated earlier, much earlier in this semester, ladies and gentlemen, in general, when you have a polynomial function, the domain is always what? Anybody remember? For any polynomial function, the domain is always anybody remember? This is a polynomial function. It's a quadratic function. The domain of all polynomial functions is always going to be all real numbers. So that's the domain of function P. What would be the domain of function R? Function R is also a polynomial function. It happens to be a linear function, but it's a polynomial function. So its domain is also all real numbers. So therefore, what's the domain of this new function called P minus R that we formed? Well, the domain of that is going to be the intersection of the domains of the component functions. So what's the intersection of these two domains? The intersection of all real numbers with all real numbers is going to be all real numbers. And you can clearly see that that is the case because P minus R of X itself is a polynomial function. No surprise then that its domain is also all real numbers. Okay? Any questions about problem number 20 there? All right, let's see what other one we got here. That was like number 20. Problem 22, they want us to form this product function called R times Q of X. Well, that's going to be R of X times Q of X, according to how we form the product function. So this product function, R times Q of X, is going to be R of X times Q of X. But what's R of X? R of X is defined to be this linear function, negative 3x, times Q of X. But what's Q of X? Anybody got the book open to that page? Square root of 1 minus x. That's what Q of X is. So R of X times Q of X is going to be negative 3x times the square root of 1 minus x. So there you have it. That would be the brand new function called R times Q of X. It would be negative 3x times the square root of 1 minus x. And now, ladies and gentlemen, what would be the domain of our product function R times Q? Well, the domain is going to be the intersection of the domain of function R and the domain of intersection, the domain of function Q. So what's the domain of function R? Where R of X, of course, is our linear function, negative 3X. Negative 3X is a polynomial function, so its domain is all real numbers. What's the domain of function Q? Where Q of X is the square root function of 1 minus X. What's the domain of the square root of 1 minus X? Recall that the domain of a function is a set of all real numbers for which a function is defined. When would this square root function ever become undefined? Anybody? When would it ever become undefined? When would it no longer be a real number?
If it was negative,
If you're taking the square root of a negative quantity, correct? So in order for this function Q of X to be defined, we need to force the radicand, this 1 minus X, to be non-negative. In other words, we need to require that 1 minus X be greater than or equal to 0, which implies then that, ladies and gentlemen, that X would have to be less than or equal to 1. So the domain of function Q requires that its input value X has to be or any real number less than or equal to 1. If you try to put any value in larger than 1 in this function, it will not give you a real number output. It will be an imaginary or complex number output. So the domain of function Q is from negative infinity up to 1, but less than or equal to 1. Now, ladies and gentlemen, what's going to be the domain of this new product function R times Q of X? Well, the domain of it has to be the intersection of the domains of functions R and Q. What's the intersection of these two domains? What set of numbers do these domains have in common? Anybody?
negative infinity up to and including 1.
Exactly. Negative infinity up to 1 and including 1. That would be the intersection of these two sets, the overlap. That would be the domain of your product function. Okay. And this should be infinity, negative. That should be negative infinity. Okay. Any questions how we A, formed a new function called R times Q of X, and B, how we determine the domain? This should be negative infinity up to 1. All right. All right. Any questions so far how we're forming new functions from pre-existing functions? All right. Well, let's try another one here. Let's try to form the function P over Q of X, number 25. And again, we're going to assume the functions have the same definition as they do for all the other ones here. So for 25, we're going to try to form this quotient function P over Q of X. And ladies and gentlemen, how do we form this function? Well, this quotient function P over Q of X is going to be formed by taking the output of function P, which is P of X, and dividing it by the output of function Q, which is Q of X. But what was function P? And what was function Q? Do you remember what those functions were? What was P of X?
P was X squared plus 3X.
All right, hold on a second here. P of X is X squared plus 3X?
Yes, and then Q was square root of 1 minus X.
Okay, thank you. So therefore, to form this quotient function, we're going to take P of X, which is to say X squared plus 3X, and divide it by the output of function Q when you put X into it, which gives you an output of the square root of 1 minus X. And this is your brand new function called your quotient function, P divided by Q of X. Now, what is going to be the domain of this quotient function, P divided by Q of X? Well, it's got to be the intersection between the domains of function P and the domain of function Q. The domain of function P, since P is just an ordinary polynomial function, is going to be the set of all real numbers. What's the domain of function Q? I think we just answered that question previously. The domain of function Q requires that X be what? Less than or equal to, what was it, 1?
Yeah.
So that's the domain of function Q. Now, I have a question for you. What would be the intersection of these two sets here? Because that's going to be the domain of our new function called P divided by Q of X. Well, the intersection of these sets is going to be from negative infinity up to 1, including 1. But ladies and gentlemen, I still claim that we have to exclude, wait a minute here. Hold on, let me think here for a second. Oh, I think we're good there. All right. Okay. Now, no, I do claim that we have to exclude one other value from our domain of our quotient function. Which value is it? Anybody? We can't just say the domain of this is from negative infinity up to 1, including 1. Why is this an error to say that this is the domain of our quotient function, P over Q of X?
Because the bottom can't be 0.
Yeah, the problem is this domain or this interval of numbers contains 1. And ladies and gentlemen, when you try to evaluate this quotient function at 1, I think we're going to get into trouble here. Because our denominator is going to become what? 0. Do you agree? And you cannot divide by 0, undefined. So this domain has to be tweaked. We have to throw out 1. So the domain of this function can't be this of our quotient function. It's got to be from negative infinity up to 1, but not including 1. You see that? We must exclude 1. That would be the proper domain of our quotient function called P over Q of X. Does that make sense? All right, so given any two functions, ladies and gentlemen, we should be able to form, any one of our functions, our difference function, sum function, quotient, or product function, and also determine the domain of the new function as being the intersection of the domains of the pre-existing functions. All right, and here's some other problems here to do these. Okay. Okay, hold on a second. All right. They're just giving you more functions defined here. S of X, T of X, and V of X are defined accordingly. And then they're going to have you using those functions form new functions like S times T of X, S divided by T of X, X plus T of X, S minus T of X, and S times V of X, and V divided by S of X. Does anybody want to see any of these problems done here? 27 through 32. Is there one that you would really like to see done?
Can you do 32?
All right, we'll look at 32. Now, to do 32, we're going to need to know what function S of X is, and it's this rational function X minus 2 divided by X squared minus 9. We're also going to need to know what function V of X is. V is in Victor, and it's going to be this square root function, the square root of X plus 3. Okay, so armed with those functions, they want us to form this new function here called, gosh, I forgot what it was. What was it, V over S or S over V? I think it was V over S. Anybody have the book in front of them? Was it V over S or S over V? Well, I forget, so I gotta look at it. It's V divided by S of X. Okay, so they want us to form this new function called V divided by S of X, which is going to be the quotient of the outputs of the individual functions. So V of X divided by S of X. But what's V of X? V of X is the square root of X plus 3. You put X in the function S, what does it give you out? It gives you out this rational expression, X minus 2 divided by X squared minus 9. But it's very awkward to leave this looking this way. So maybe we should try to, maybe simplify it a little bit. What this is saying is to take the square root of X plus 3 and divide it by this rational function, which is x minus 2 over x squared minus 9. How do we divide fractions? Change division to multiplication, flip the second fraction upside down. And therefore, the quotient function v over s of x, or v divided by s of x, is going to be it's going to be this x squared minus 9 times the square root of x plus 3. And that's going to sit over x minus 2. All right, so ladies and gentlemen, that is your brand new function called v divided by s of x. And what would be the domain of this brand new quotient function v divided by s of x? Well, to determine that, we're going to need to know the domain of the individual functions. So what was the domain of function s? What's the domain of function s up here, ladies and gentlemen? Being a rational function, we got to make sure that function s of x never has a division by 0. So we have to insist that x squared minus 9 never be equal to what? 0. So therefore, x squared minus 9 cannot be equal to 0, which is saying x squared cannot be equal to 9, which when you take the square root of both sides of this quadratic equation, it's saying that x cannot be equal to positive or negative 3. So the domain of function s, ladies and gentlemen, is all real numbers except 3 or negative 3. If you try to put 3 or negative 3 in the function s of x, the denominator becomes 0. The whole function is undefined. So the domain of function s is from negative infinity up to negative 3, but not including negative 3, in union with not including negative 3, up to 3, but not including 3, in union with not including 3 up to infinity. That is the formal interval notational way of representing the domain of function s. Notice it's all real numbers except negative 3 and positive 3. Those values are excluded from its domain. Now, what's the domain of function v? What's the domain of function v? Well, function v is defined to be a real number just so long as this x plus 3 never becomes negative. As soon as this x plus 3 becomes negative, then you're going to be taking the square root of a negative, which is no longer a real number, but it's called an imaginary number or a complex number. So in order for this function to be defined, we must require that this x plus 3 be greater than or equal to 0, which when you solve this inequality for x implies that x must be greater than or equal to negative 3. So the domain of function v is all real numbers equal to negative 3 or greater than negative 3. That would be the domain of function v. Now I have a question for you, ladies and gentlemen. What would be the intersection of those domains? So the domain of this quotient function v over v divided by s is going to be the intersection of the domain of function v and the domain of function what? S. What's the intersection of this domain and this domain? Can we see what the intersection would be of these two domains? Well, this domain, okay, goes from negative 3 up to infinity, including negative 3. This domain does not include negative 3. And it also does not include what? Positive 3. But notice negative 3 is in this domain and positive 3 is in this domain. So the intersection of this domain and this domain would be all real numbers greater than negative 3 up to 3, but not including 3. And then all real numbers strictly greater than 3. So the intersection of these two domains is going to be from negative 3 up to 3, not including negative 3 or 3, in union with not including 3 up to infinity. That would be the domain of your quotient function v divided by s of x. Questions, ladies and gentlemen, how we are doing this? Or wait a minute here. Have I missed anything? All right, if you look at the quotient function, v divided by s of x. This isn't the domain at all. Why is that not the correct domain for a quotient function? Granted, the domain of function s excludes 3 and -3, and the domain of function v requires that x be greater than or equal to -3. But ladies and gentlemen, when we do the division with function v with s, we get this new function right here. What would be the domain of this function here, this quotient function? It's not the intersection at all. I'll tell you why it can't be the intersection at all. Number one, -3 and 3 would be included in the domain for this quotient function. But notice 2 cannot be in the domain of this quotient function because the denominator would become 0, whereas 2 was in this interval here. So we don't have that correct. What is the domain of our quotient function? What numbers can it not have in it? So what numbers would cause this to be undefined?
Anything less than -3 and +2, or yeah, +2.
Notice, yeah, any real number that's less than -3 would cause this to be undefined because it would no longer be a real number. And we cannot have 2 in our domain either, because if x is 2, this function, this quotient function is undefined because the denominator would become 0, and you cannot divide by 0. So the domain of our quotient function would have to, ladies and gentlemen, include all real numbers from -infinity up to -3. Now, what did I say the domain of this was here? X plus 3 would have to be greater than or equal to what? 0, correct? Which says x must be greater than or equal to what? -3. So to satisfy this square root in our quotient function here, we would have to make sure that x is greater than or equal to -3 to ensure that this does not become non-real. Okay, well, we'll do that. -3. Up to what though? Remember, we must exclude 2 though from the domain because your denominator would become 0 if x is 2. So we could go from -3 up to 2, but not including 2, in union with not including 2 up to what? Positive infinity. This would be the domain, ladies and gentlemen, of this quotient function here. Okay, that would be the domain. Make sense how we reasoned out the domain of that quotient function? So you cannot put any value into the quotient function that is less than -3. And you cannot have 2 in this domain of this quotient function, okay? All right. I got a question. Is anybody in here going into calculus someday?
Yes.
All right, we got one person. Anybody else gonna maybe take some calculus? Or is that
Possibly.
it? What's that?
Possibly.
Possibly, okay. Well, you're not gonna go far in calculus 1 without running into this construct here. This is called the difference quotient. It's different than the difference function. This is called the difference quotient of a function. And this is going to become of paramount importance when you start easing into something called the derivative of a function in your first semester of calculus. And let's see if I can draw a picture of this. I used to have a ruler, but my ruler is gone. Somebody swiped it. All right, so suppose that we have the graph of a function in the XY plane. And suppose, suppose, ladies and gentlemen, that the function looks like this. Okay, so that's the graph of a function in the XY plane. And suppose the interval of interest is AB here on the x-axis, AB, right? Suppose we want to compute the average rate of change of this function on the interval from A to B. Well, the average rate of change of this function on the interval from A to B is going to be the slope of this line segment there. See that line segment there? This line segment, ladies and gentlemen, is called a secant line. A secant line. That's what that line is called, a secant line. And we would therefore say the average rate of change of this function f on the interval AB would be the slope of the secant line with endpoints of f of A, and the other endpoint is going to be B f of B. So ladies and gentlemen, if I put A into this function, I get out something called f of A. If I put B into this function, I get out some output value, which would be f of B. So this point here is going to be B f of B. This point down here is going to be A f of A. Well, ladies and gentlemen, how do we find the slope of a line in the XY plane? Well, slope is rise over run. Do you agree? It's a measure of the amount of rise you experience or fall versus the amount of run you experience as you move from one point to another point on the line. So if I build this right triangle here, the amount of rise we will experience as we move from this point down here at x equals A up to this point x equals B along this secant line, the amount of rise we experience is going to be the difference in the y coordinates, which is going to be f of B minus f of A. The amount of run we experience is going to be the change in x from A to B, so it's going to be B minus A. Therefore, ladies and gentlemen, the slope of the secant line in my drawing here is equal to the change in y over the change in x. It's the amount of rise versus the amount of run. In particular, it's going to be the change in the y coordinates, f of B minus f of A divided by B minus A. Okay. That's what it's going to be here. And this slope here is going to be equal to the average rate of change of f with respect to x on the interval AB, on the interval from A to B. Everybody see that there? Okay, that's called the average rate of change of this function with respect to x on the interval from x equals A to x equals B. The average rate of change of this function is nothing more than the slope of the secant line here. All right, now, that's the average rate of change of that function there. Okay. Normally, ladies and gentlemen, we let this b minus a here, we let it represent a number called h. Okay, h. And so, if we want to compute the average rate of change in general of any function from x to some other value or other point on the graph, which is x plus h here, we want to find that average rate of change. Again, it's going to be the slope of this secant line here. So the interval in question in general now is x to x plus h here. All right. And therefore, we say the difference quotient of function f on the interval from x to x plus h is going to be f of x plus h minus f of x divided by x plus h minus x, which simplifies to f of x plus h minus f of x divided by just h. Where this point here is the point x plus h, f of x plus h. And this point down here is the point x, f of x. So again, the slope is rise over run, correct? So the amount of rise you experience is the difference between the the y coordinates rather, which is to say f of x plus h minus f of x. And the amount of run you experience is the difference between the x coordinates, which is x plus h minus x, which just gives you h there, okay? So this is called the difference quotient, ladies and gentlemen, for any function f of x. And this becomes extremely important when you start looking at the derivative of a function. The derivative of a function is going to be the limit of this difference quotient as h approaches 0, okay? Or as this point x plus h moves closer and closer from the right towards point x here. What happens is x plus h moves closer and closer to point x here, is these secant lines are going to get shorter and shorter here. And ultimately, these secant lines, ladies and gentlemen, are going to approach what's called a tangent line that touches this graph precisely at one point at x equals x here. And the limit as h approaches 0, or the limit of this slope of our secant line approaches the slope of this tangent line. And the slope of this tangent line at x equals x is the derivative of function f of x evaluated at x, okay? So that's what the first derivative is all about. All right, so this difference quotient, now we're not going to do differential calculus in here because this is just algebra, but this difference quotient, ladies and gentlemen, is for problems 33 through 36 here. They want you to find the difference quotient in part B for each of these functions here. And I am going to demonstrate that for one of these functions, maybe like number 36. We'll look at this quadratic function and we'll try to compute the difference quotient for it. And the difference quotient is this ratio right here, this quotient. All right. So the instructions will say find f of x plus h minus f of x divided by h, or the function f of x equal to x squared minus 3x. So that's what we're going to attempt to do. Okay, so this is what we're going to try to do here. Well, how are we going to do that? Well, first of all, we need to find f of x plus h. What does it mean to find f of x plus h? Well, that means we need to put x plus h in the function f. So wherever we see x in the definition of this function f of x, we have to replace it with the input value of x plus h here. So x plus h has to drop in here, and it has to drop in here. So this x plus h here has to go in here for x, and also for here and for x. So f of x plus h is going to be x plus h squared. X plus h squared minus 3 times x plus h. All right, and we can simplify this here if you want. You're going to have to FOIL this out, right? X plus h times itself. And here you can distribute the -3 inside the parentheses. So you got minus 3x minus 3h. Now what's x times x? That gives you what? X squared. X times h is plus xh. H times x is plus another xh. And then h times h is plus h squared. Hence we have x squared. Xh plus xh is going to combine to give you 2xh plus h squared minus 3x minus 3h. That's what f of x plus h is going to be. And so we're going to take this expression here and put it back into the difference quotient for f of x plus h. So f of x plus h is replaced with this, okay? So therefore, f of x plus h minus f of x divided by h is going to become what? In for f of x plus h, we put all this. So we got x squared plus 2xh plus h squared minus 3x minus 3h. And then we have to minus off f of x. But what's f of x? F of x is x squared minus 3x. So we got to subtract off x squared minus 3x. All of this is then to be divided by what? H. Now the good news is whenever you evaluate the difference quotient, ladies and gentlemen, for a function, and again, this is called the what? This is called the difference quotient. Whenever you evaluate the difference quotient for a function, the good news is you always get cancellation. Terms always drop out. And so therefore, simplifying this difference quotient, we can distribute the negative sign in here. So we're going to have x squared plus 2xh plus h squared minus 3x minus 3h minus x squared plus 3x. And this all sits over what? H. Now what drops out in the numerator? Anything? What cancels out? Well, not the x squareds. We got this 3x here that drops out with this 3x, and we got this, wait a minute, I sit corrected. The x squareds do cancel out, don't they? They are gone. So the x squareds drop, the 3x's drop, all that cancels out. And so how does our difference quotient simplify for this function f of x? Well, heck, we're just left with what? 2xh plus h squared minus 3h, and all this is divided by what? H. Can we further simplify this? The answer is yes. We can factor h out of each term in the numerator, leaving behind h times 2x plus h minus 3. And what happens to the h's now? They drop out. And you'll see in your first semester in calculus, when you start looking at the definition of the derivative of a function, you'll see that it's very important that these h's do drop out, critical in fact. So ladies and gentlemen, the difference quotient for this quadratic function is going to be 2x plus h minus 3, and that's your answer, okay? That is your difference quotient for the function of f of x equal to x squared minus 3x. We just evaluated the difference quotient for this function. And your answer is 2x plus h minus 3 in the end. Any questions how we evaluated that difference quotient for that particular quadratic function? That's exactly how you would evaluate the difference quotient for all the other functions. So So nothing changes. The only thing that changes is what kind of function you're working with. For instance, 34 is just a linear function. I did number 36, which is a quadratic function. Would anybody else want to see another one like that done, or is that one good enough for this difference quotient here? Anybody want to see a linear function evaluated for the difference quotient?
Sure.
Which one? Take your pick. 33 or 34 or 37?
34.
All right, so 34, our linear function is f of x equal to 8x plus 4. And given that linear function, they want us to find the difference quotient for it, which is f of x plus h minus f of x divided by h. So first of all, you might want to find f of x plus h. And in fact, for part A of this question, they have you do that separately anyways. So f of x plus h means we're going to put what into this function? What's going into this function? We're going to put what? X plus h. So that takes the place of x in the definition of the function. So f of x plus h is going to be 8 times x plus h plus 4. That's what f of x plus h is going to be. Which means when we distribute the 8 inside the parentheses here, we're going to have 8x plus 8h plus 4. That, ladies and gentlemen, is what f of x plus h is going to be. Any questions how we found f of x plus h? We found this part of our difference quotient. Found that first. So that being the case, our difference quotient now will take that value of f of x plus h. So in place of f of x plus h in my difference quotient, that's what this whole thing is called. This construct is called the difference quotient. F of x plus h is going to be replaced with 8x plus 8h plus 4. And then we're going to have to subtract off f of x, but f of x is just 8x plus 4. And all this is divided by what? By h. Now remember I said you're always going to get cancellation when you evaluate or find this difference quotient for a function. And therefore our difference quotient is going to be 8x plus 8h plus 4. Distributing the negative sign in the parentheses, we have minus 8x minus 4. Notice the 8x's drop out, the 4's drop out, and we're left with 8h over what? H. And what happens to the h's? They cancel out. So ladies and gentlemen, your answer is 8. The difference quotient for this linear function, f of x equals 8x plus 4, is equal to 8. Hey, does anybody recognize what 8 is? How does 8 relate to the linear function up here, ladies and gentlemen? Do you see it? How does 8 relate to the linear function? F of x equals 8x plus 4. Anybody see it?
It's the number of x.
What is that called? For a linear function, what's 8 called?
The slope.
The slope. Ladies and gentlemen, isn't 8 the slope of this linear function? Look at that. And we got 8 for our difference quotient for that linear function. Just a coincidence? The answer is absolutely not. Has to be 8. Because if you graph 8x plus 4 in the xy plane here, the graph is going to be this right here. And if you choose some interval x to some other interval x plus h, so if you choose the interval from x to x plus h, you can see that the slope of this secant line that connects these 2 points is going to be the slope of the is going to be equal to the slope of the line itself. So the slope of the secant line on the interval x to x plus h is equal to the slope of the line itself. So there's no small wonder then why the difference quotient for this linear function did not give us the slope of the line itself, 8, because that's going to be the slope of the secant line. The difference quotient is the slope of the secant line, ladies and gentlemen, that connects the endpoints of x and x plus h. This line segment has to have that, it has to have the same slope as the line itself. That makes sense. So what would be the difference quotient for g of x if g of x is equal to 3x plus 5? What would be the difference quotient for this linear function? The answer would be 3. The slope of the line equal to the slope of the line. If I wanted you to find a difference quotient for a function m of x, which is -2/5 x plus 10, what would be the difference quotient for function m of x? -2/5 would be the answer, because that's the slope of the line. That's also the slope of the secant line at any interval for that linear function. Okay. Well, that's your difference quotient. You will run into that again in calculus 1. All right. Classwork number 1, ladies and gentlemen. Classwork number 1. Given the function f of x is defined to be -2x, this linear function, g of x is defined to be this absolute value function of x plus 4. And h of x is defined to be this rational function. H of x is defined to be the rational function 1 over x minus 3. Problem number 1 for classwork 1. I want you to find this difference function, f minus g of -1. And I want you to evaluate it at -1. Well, what does that mean? Well, first of all, what it means, ladies and gentlemen, is you got to find, first of all, the difference function for f and g. So first of all, you want to, I'll give you a hint. First, you got to find f minus g of x. First, you got to find the new function called f minus g of x. Then you evaluate it at x equals -1. And that will give you f minus g of -1. So first, you got to find the difference function. And then you plug in -1 into it to find f minus g of -1. So you guys can do that one. Then I want you to find g divided by h of 0, which means here's a hint. First, you got to find g divided by h of x, which is going to be g of x divided by h of x. Then you want to let x be equal to 0, and you want to evaluate the function. Question number 3, g plus h of 0. And question number 4, I want you to find f times g, and then evaluate this at -5. Okay. So again, before you actually evaluate these new functions we're forming, you might want to just find the function first, then plug the value in to evaluate it. So like for number 4, hint is first find f times g of x, then let x be equal to -5, and then evaluate the function. All right. So classwork number 1, see if you can do these problems here. Well, I'm just going to call, we'll call it classwork 1 here. There might be a classwork 2. We'll go with that first. Can you see all these problems in their entirety right there? All right. There we go. Classwork 1, ladies and gentlemen. Anybody get F minus G of -1? Caleb, did you get that one?
I wasn't really sure how to do it with the absolute values. So I broke it down into 2 minus the absolute value of 3, but I didn't know where to go from there.
All right, what's the absolute value of 3?
3,
3. So you got 2 minus
Just
3,
go
which is
straight to
what?
-1.
Yeah, -1.
Okay, I wasn't sure if we had to do something to get it out of the absolute value or not.
So F minus G of -1, first you might want to find F minus G of X, which is the new function called -2x minus the absolute value of X plus 4. Then to evaluate that function at -1, you simply put -1 in wherever you see X. So -2 times -1 minus the absolute value of -1 plus 4. which is 2 minus the absolute value of 3. Absolute value of 3 is 3. So 2 minus 3 is -1. Your answer should be -1 for problem number 1. Number 2, g divided by h evaluated at 0. G divided by h of 0. First, you want to find the function g divided by h of x, which is g of x over h of x, which is nothing more than the absolute value function divided by this rational function. And this x minus 3 is going to come up in the numerator then and get multiplied by the absolute value of x plus 4. To evaluate it now at 0, all you got to do is put 0 in for x here and here. 0 minus 3 is -3. 0 plus 4 is 4. The absolute value of 4 is 4. 4 times -3 is -12. Did anybody get -12 for number 2? -12. Number 3, g plus h evaluated at 0. What is g plus h of x? It's a new function called g of x plus h of x, which is to say the absolute value of x plus 4 plus 1 over x minus 3. To then evaluate it at 0 means to put 0 in here for x and here. So we have the absolute value of 0 plus 4 plus 1 over 0 minus 3, which is the absolute value of 4 divided by 1 over -3, which is 4 minus 1/3, which is really 12/3. Another name for 4 is 12/3. 12/3 minus 1/3 is 11/3. Anybody get 11/3 for number 3? Problem number 4, f times g of -5. What is f times g of x? It's going to be f of x times g of x, which is -2x times the absolute value of x plus 4. Now we evaluate it at -5 by putting -5 in here and here. So -2 times -5 times the absolute value of -5 plus 4. There's going to be 10 times the absolute value of -1. The absolute value of -1 is 1. 1 times 10 is 10. The answer is 10. Anybody get 10 for number 4? All right, so there you go, ladies and gentlemen. Classwork number 1. Forming new functions from pre-existing functions and then evaluating them at some specific input value. Okay. Let's see if we can do some composition of functions now. So let's scroll on down here. All right. In problems 47 through 62 here in the textbook, they give you functions f of x, g of x, and h of x defined accordingly. And then they're going to have you, using the composition operator, they're going to have you find compositions of these functions and then evaluating them also. So we got a cubic function for f of x. We have a square root function or a radical function for g of x. And we have a linear function for h of x. For problem number 47 here, they want us to find f of g of 8. What is f of g of 8? Well, first of all, you could find f composed with g of x, which is going to be f of g of x. Which says when you put x in the function g, you get out g of x. What's g of x? The square root of 2x. So the square root of 2x then becomes the input in the function f. So g of x is square root of 2x. Now we take the square root of 2x, which is the output of function g. It now becomes the input in the function f. So we take this square root of 2x, and wherever we see x in the definition for function f, we replace it with the square root of 2x. Square root of 2x goes in here, and the square root of 2x goes in here. So f evaluated at the square root of 2x is going to be equal to the square root of 2x cubed minus 4 times the square root of 2x. That's your brand new function called f composed with g of x. F composed with g of x. And now they want you to evaluate this function at what? 8. So that's what this is saying to do. F composed with g of 8. So that means we can put 8 in here and here. So we'll have the square root of 2 times 8 cubed minus 4 times the square root of 2 times 8. And what does this evaluate to? Well, 2 times 8 is 16. The square root of 16 is what?
4.
4, and then we're going to have to cube that. Here we have 4 times the square root of 16. So the square root of 16 is 4, and then 4 has to be what? Cubed. And this is going to be 4 times 4. 4 times 4 is 16 times 4 is 64. So 4 cubed is 64. 4 times 4 is 16. 64 minus 16 is going to net us what with what? It'll be 8, 48, I believe. And that's what F composed with G of 8 is going to be equal to, is 48. Any questions how we did that problem? That's F of G of 8. All right. Let's try number 48, H of G of 2. H of G of H of G of 2. This is really going to be H composed with G evaluated at 2. That's what it is. First, you might want to find what that function is. H of G, H composed with G of X is H of G of X. Put X in the function G, out comes G of X. G of X is the square root of 2X. The square root of 2X, then the output of function G becomes the input in the function H. So H takes the square root of 2X, replaces X in its definition with it. So we're going to have 2 times the square root of 2X minus 3. That's the brand new function called H composed with G of X. This is H composed with G of X. Now they want you to evaluate it at 2. So that means we just replace X with 2. So we're going to have 2 times the square root of 2 times 2 minus 3. 2 times 2 is 4. And the square root of 4 is what? 2. 2 times 2 is 4. 4 minus 3 is 1. Answer, ladies and gentlemen, is 1. So H of G of 2, which is really H composed with G of 2, is going to be 1. Questions how we got that? All right, I'm gonna. Oh, that was one like 48 there. Maybe we could try 54. Using the previously defined functions, let's find H composed with F of -2. H composed with F of -2. So first of all, what is the new function H composed with F of X in general? Well, that's going to be H of F of X. Put X in the function F, out comes F of X. But what's F of X? You put X in the function F, out comes X cubed minus 4X. That's F of X. So this output from function F, this X cubed minus 4X, now becomes the input in the function H. What does H do to its input? It doubles it and subtracts 3. So this X cubed minus 4X takes the place of X in the definition of function H right here. So we're therefore going to have 2 times X cubed minus 4X minus 3. That's your brand new function here called H composed with F of X right here. And you know, you can distribute the 2 inside the parentheses if you want to do that. So you'll have 2x cubed minus 8x minus 3. Now they want you to evaluate this new function at -2, which is to say we replace x here and here with -2 and then evaluate. So this function evaluated at -2, this h composed with f, is going to be 2 times -2 cubed minus 8 times -2 minus 3. What's -2 cubed? -2 times -2 times -2.
-8.
And -8 times 2 is -16. Minus 8 times -2 is +16. Minus 3. Answer is, ladies and gentlemen, -3. So that's what h composed with f of -2 would be. It would be -3. Any questions how we computed that? Here they give you the definition of 4 functions, M, N, P, Q, and R. And then they're going to ask you to form, compositions of these functions. So what would be P composed with N of X for number 66? P composed with N of X is going to be what brand new function? Well, it's going to be P of N of X. But what's N of X? It's defined to be this linear function x minus 5. So we're going to find this new function called P composed with N of X, which is P of N of X. Put X in the function N, out comes N of X, which is x minus 5. X minus 5 now becomes the input in the function P. But how was function P of X defined? How was that defined? P of X is x squared minus 9x. So P of X is x squared minus 9x, this quadratic function. And we're putting x minus 5 into function P. That means this x minus 5 now has to come over here and it has to take the place of x in the definition, wherever it's found in the definition of P of X. X minus 5 drops in here and it drops in here. So function P evaluated at x minus 5 is going to be x minus 5 quantity squared minus 9 times x minus 5. You are looking at your brand new function called P composed with N of X. P composed with N of X. Your brand new function. Furthermore, if I wanted you to evaluate this function at, let's say, 0, that means you'd have to replace x with 0 wherever you see it in the definition of this new function. So 0 drops in here and here, in which case you'd have 0 minus 5 squared minus 9 times 0 minus 5. 0 minus 5 is -5. -5 would have to be squared. Minus 0 minus 5 is -5. What's -5 times -5? 25, and minus 9 times minus 5 is plus 45. And hence we would get 70. So P composed with N of 0 would evaluate to 70 for those functions. Any questions how we're working with these compositions of functions, forming a function, a composition of functions from pre-existing functions? You know, we could also do these compositions. We could form them, ladies and gentlemen, from graphs too. For instance, in these problems here, in this problem number 99, they give you the graph of 2 functions, f of x in blue and g of x in red. And then they're going to ask you a whole bunch of questions with regards to those functions. So problem number 99A. Using the two functions that are defined in the graph, they want you to find f plus g, and they want you to evaluate that sum function at 0. Well, ladies and gentlemen, this is really going to be f of 0 plus g of 0. But what's f of 0? We got to go to the graph, put 0 in the function f, and then read off what its y coordinate would be. So f of 0 is going to be what? Using the blue graph. We go out on the x-axis to 0. We put 0 in the function f. What do we get out? What's the y coordinate of this point up here on the blue graph that has 0 for its x coordinate? What's f of 0? What's f of 0 equal to? Anybody?
3.
3. F of 0 is 3. Plus, what's g of 0? Now, g of 0 has us putting 0 in the function g, which we start on the x-axis at 0 and go down and strike a point on the red graph, which is a graph of g of x. What do we get out when we put
-2.
0 in? Yeah, we put 0 in the function g, we get out -2. Therefore, we can answer this question. Therefore, it must be true then that f plus g of 0 must be f of 0 plus g of 0, which is to say 3 plus a -2, which gives us 1. That's your answer. F plus g of 0 is 1. Let's try B. Using those graphs defined, those functions defined as graphs. B, they want us to not only form this difference function, g minus f, but they want us to evaluate it at 2. So g minus f of 2 is what they want us to find. Well, what is going to be g minus f of 2? That's going to be g of 2 minus f of 2. But ladies and gentlemen, what's g of 2 and what's f of 2? We got to go to the graphs and find out. What's g of 2? We go on the x-axis out to 2. Then we have to strike a point on the red graph, which is right here. So what is g of 2 equal to? You put 2 in the
0.
function g of x, yeah, and you get out 0. So g of 2 is 0. You put 2 in the function g of x, the y coordinate of which is the output is 0. G of 2 is 0. So g of 2 is 0 minus what's f of 2?
1.
Now we go back to the graph, go out on the x-axis to 2, and then we go up and strike a point on the blue graph, which is the graph of f of x. Notice its y coordinate at this point is 1. So you put 2 in the function f of x, out comes f of 2, which is 1. F of 2 is 1. 0 minus 1 is -1. Your answer for B is -1. That's your answer for B, -1. We understand what's going on here so far, ladies and gentlemen. Let's try another one. All right, let's try C. For C, they want you to find G times F of -1. G times F of -1, which is really G of -1 times F of -1. But we got to find what G of -1 and F of -1 are. So we have to go and use the graphs of those functions to find out. We put -1 into these functions. So we go to the x-axis at -1. What would be G of -1 then? Go down and strike the red graph at this point. What's the y coordinate of this point down here?
-2.
-2. So G of -1 is -2. Times what's F of -1?
3.
Go to the x-axis -1, go up and strike the blue graph at a point. What's the y coordinate of this blue graph? 3. So f of -1 is 3. You put -1 in the function f of x, it gives you out 3. So therefore, we have -2 times 3. Your answer is -6 for part C. G times f of -1 evaluates to -6. D. What's question D? Now they want us to do G divided by f of 1. G divided by f and evaluated at 1. That's going to be g of 1 divided by f of 1. But we got to find g of 1 and f of 1. So we have to go back to the graphs of the functions to find them. So what's g of 1? Put 1 into function g, out comes what?
2
One.
or -1, sorry.
G of, yeah, g
Oh,
of
negative
1.
one.
G of 1 is -1. What's f of 1?
2.
1 in the
2.
function f, you get out 2. So g of 1 is -1 and f of 1 is 2. So we'll have -1 divided by 2. That's your answer. So g divided by f of 1 is -1/2. Questions on that one? Question E. Now they want us to form, or they want us to find f composed with g of 4. Ladies and gentlemen, this has nothing to do with f times g of 4. The composition operator is not even related to the multiplication operator. Don't think that's multiplication. No, f of g of 4 means that we have to find f of g of 4. Which means, first of all, we got to find function g evaluated at 4. What's g of 4? We go to our graph to find out. So we put 4 in to function g, and what do we get out? You put 4 in and you get out what?
2.
2. So g of 4 is equal to 2. G of 4, which is 2, now becomes the input in the function f. So now we have to evaluate, see, g of 4 we found was 2 from the graph. Now 2 becomes the input in the function f. So what's function f evaluated at 2? We got to go back and find out. So you put 2 now in the function f. You go up and strike the blue graph, which is f of x. What is the output?
1.
1.
1. So f evaluated at 2 is 1. Hence, our answer to this problem is 1. So f composed with g of 4 is 1. Do we see how the composition operator is working? The output of one function, which is g evaluated at 4, which is 2, becomes the input into another function called f. Okay? That's how composition works. All right, what's part f? G composed with f of 0. So part f, g composed with f of 0. Well, that's gonna be, that's really gonna be g of f of 0. So first we're gonna put 0 in the function f, and we have to go to the graph and read out what it gives us out. What is f of 0? We gotta find what f of 0 is.
3.
Put 0 into function f, yeah, you get out 3. So f of 0 is equal to 3. The output of function f at 0, which is 3, now becomes the input in the function g. 3 goes in the function g now. Because f of 0 we found from the graph is 3. So 3 now goes in the function g. So what's g of 3? G of 3 is going to be
2.
1, right? G of 3 is 1.
Mhm.
You put 3 in the function g and you get out 1. So, ladies and gentlemen, you got your answer. It should be 1. So g composed with f of 0 evaluates to 1. Questions how we're doing these using these graphs here. I got a question. If I had my functions g and f defined according to some tables with ordered pairs, could you also do these problems from tables instead of graphs? Do you think you can do that? If our functions were defined according to tables of ordered pairs, we could also do the same problems. We don't necessarily even need the graphs anymore. So you can
I
do
think so.
You can do from the graphs or what? A set of ordered pairs, correct?
Mhm.
Answer all these questions. All right, so what would be g of f of 4 for g? Well, first we have to find function f evaluated at 4. So what's f of 4? Put 4 into function f. What do you get out?
-1.
Yeah, f of 4 is -1. So f of 4 is -1. So -1, the output of function f becomes now the input into function g. So what's g of -1? See, f of 4 was -1. -1 now goes into function g. And so what's function g evaluated at -1? -1,
-2.
-2. Function g evaluated at -1 gives you an output value or a y coordinate value of -2. So your answer is -2. Okay. Questions how we did these problems here, ladies and gentlemen? All right, guess what classwork number 2 is going to be? It's going to be one just like this. In fact, ladies and gentlemen, I want you to do this problem here. I want you to do problems 100A through G using these graphs for f of x and g of x. So classwork number 2 is problem 100A through G. See if you can evaluate those using those graphs, okay? That'll be classwork number 2. Well, we got these. Anybody get A? Check these over, and this is what I'm getting here. I also added another problem at the end here. F, you can compose a function with itself. F composed with f of -3, as it turns out, it's going to be -1. But might want to try that one for practice. F composed with f of -3. Let me know if you're not getting any of these, ladies and gentlemen. Are we getting any of these? Just gonna check them over, check my work too, so.
C is the only one that I had something different for.
Yeah, because what did I do with C that I should not have done?
You switched it to G of F of 2.
Yeah, I fell into the trap that I don't want you to fall into, ladies and gentlemen. This is not supposed to be G composed with f of 2. It's supposed to be G times f of 2. This is all bogus. What it should be is G of 2 times f of 2. Okay. Now, what'd you get for G of 2?
I got -1, and then I got
Times f of 2 is what?
2.
So your answer should be -2. Did we get -2 for C?
Yeah.
That's what
Yes.
it should be. So don't confuse multiplication with composition. There's a huge difference, big difference, so be careful.
I
Yep.
didn't do through H. I just did through G.
Yeah, H I added. See if you can do
Okay.
that F composed with F of -3. Convince yourself the answer is -1. So I made H up. Does it check out? H should be, is it -1? So what's F of -3? F of -3 is going to be what? -2. Then you put -2 in the function F. F of -2 is -1. So that would be correct. All right, is this making sense how we're doing? How we're given pre-existing functions, we can form new functions. Sum function, difference function, product function, quotient function, composition of functions. And also, ladies and gentlemen, I talked about the difference quotient, how you can evaluate that important difference quotient for a function, which puts you on the doorstep of differential calculus, okay? That difference quotient. Because that's what you're going to be seeing again if you take a course in calculus, as you warm up to the definition of what's called the derivative of a function. Okay. All right. Any other questions for today? That's classwork number 2. So you can send me classworks 1 and 2 anytime. And I did put, like I said, the chapter 2 quiz on Alex. It will run through up to midnight of October 21st. October 21st at 11:59 p.m. is when it's due. You have 2 tries at that quiz, and I'll take the higher of the 2 scores. Okay. Any other questions, ladies and gentlemen?
When's the exam?
Well, our first exam will be given out on the 20th of October. So in 2 days, I'll email you the first exam.
How long do we have to like complete that?
Well, the exam, let's see here. I'll probably extend the due date on the exam too, and I'll email all of you and let you know, but get it out to you by Wednesday. I can give you till maybe Saturday night by midnight. Is that good, or is that going to work for everybody?
Perfect.
The 23rd, October 23rd, 11:59 PM, the first exam will be due. Okay.
Great.
I will also indicate via email as to what I want you to specifically send me as proof of having done your chapter 1 and 2 homework. So stay tuned for that very important email. All right, any other questions?
So is there Alex homework?
Yeah, both the textbook homework, Les Ullman, and the Alex homework will be due. Well, now let me think here, because I got to get the 2.8 Alex homework out. And I have not done that yet. I did get the 2.7 out. I will update Alex with 2.8 homework. And I'll give you like to, midnight to 21st to get the Alex homework done, okay? And the textbook homework you can get to me by midnight Saturday night, October 23rd, all right? So I will email you with all this confirmation stuff here, okay? Any other questions? So Alex homework due by midnight, October 21st. Textbook homework due by midnight, October 23rd. Exam, chapter 1 and 2 due by midnight, October 23rd. The Alex quiz on chapter 2 is due by midnight, October 21st, correct?
Yep, thank you.
All right, have a good day.
You
Have a good one. Bye.